Esteemed listeners, this tutorial is about divide and conquer based algorithm design strategy, and it is number 3 in the sequence of tutorials. And in this tutorial we will discuss about the remaining examples on divide and conquer strategy, that is binary search and multiplication of large integers and other examples as we go by. So binary search is a famous linear search binary search algorithm is quite famous because of its efficiency, because of its reduction in the data, reduction in the size of the array in successive iterations. It just halves and considers only one portion of the array while searching a key. And here you should recall key is a very important component, very important figure, very important element in an array. It could be an ID in a string array. It could be an important number in a numerical array. Like we want to see whether any student has taken 99 marks in a particular subject. Then 99 becomes a key. Okay, key has to play a key role in an array, therefore it is so called. Okay, binary search in comparison with linear search demands the array to be sorted before binary search is applicable, before binary search could be applied. In every iteration it finds the middle position of the sorted array and compares the key to be searched with the element present in the mid. If there will be 3 comparisons that would happen. If therefore binary search is often called as three-way switch. Some of the authors do prefer to call this binary search to be three-way comparison or three-way switch. If key is greater than the middle element, then the array's starting point will be one position more than the mid, and the other portion will be simply discarded. If key is less than the middle element, then the right extremity of the array will be one position less than the mid position. Okay, therefore the right half of the array will be simply ignored or disregarded. If the mid element in a particular iteration of the array is equal to the middle element, okay, if the key is equal to middle element in any particular iteration of the array, the element is found and the algorithm stops. Otherwise the procedure repeats till the right extremity location becomes the more than the left extremity location. Okay, I repeat, otherwise the procedure repeats till the right extremity location becomes more than the left extremity location. This would happen if and only if the element is not present, and if and only if the key is not present, and if we try to search in the array. So we will exemplify this. We will take an example and we will see what exactly happens if we try to search a key value which is not available in the array. And of course, if the key is present anyway, the array, the middle position, okay, middle position will be struck and it will be found. If in any rotation, in any iteration, the key is equal to array mid, the key present in the middle of the array, then the key is found. Therefore, in order to find the key is to be located in the mid. Okay, anyway, if for a question as to where key is found in binary search, if at all key is present, we should say it is the mid position, okay, in that particular succession or in this particular iteration. So we will take an example to consolidate our idea regarding binary search. Here it is. So it consists of 1, 2, 3, 4, 5, 6, 7 elements, and we will the first initialization happens with respect to the initial position. So here L equal to 0, the left extremity equal to 0. This is in the first iteration I am talking about, okay, and I am explaining. And the right iteration, okay, is, okay, 0, 1, 2, 3, 4, 5, 6. Right iteration is 6. Therefore mid will be found. Okay, the location of the mid will be equal to 0 plus 6 divided by 2. 0 plus 6 divided by 2. In order to incorporate even odd elements, I think we need to put the floor. And at one side it will be longer and the other side it will be shorter. Okay, so it is 3. So mid position is 3. And let us say we are searching for an element which is 22, which is not there. Key equal to 22, we are searching. Okay, 3. So 0, 1, 2, 3. So here is the mid position. Okay, we should understand in the first iteration the mid position strikes over here, and the comparison, first comparison will be easy. A mid equal to key? No, it's not equal to key. Therefore the R, the right extremity, will be made as mid minus 1. So mid minus 1 here becomes the right extremity, and the other portion of the array can simply be disregarded because the key value is lesser than the array of mid. Okay, if the array were to be a of mid. Okay, if the name of the array were to be a, and then it goes for second iteration, L remains to be 0. Okay, left extremity remains to be 0. R has become mid minus 1, therefore it is 3 minus 1, it becomes 2. Therefore once again new mid will be, okay, the algorithm will calculate new mid will be definitely 0 plus 2 divided by 2, 0 plus 2 divided by 2, it will become 1. Okay, that will be equal to 1. So 1 is here, 0 and 1 is over here, mid is over here. Once again comparison will happen. It is not equal to a of mid, key is not equal to a of mid. Okay, therefore once again R will be shifted as mid minus 1. So R becomes before the iteration is completed, R becomes mid minus 1, that is 2 minus 1, it becomes 1. So in the next iteration L equal to 0, okay, R equal to 1, therefore mid equal to, it's an integer division anyway, mid equal to 0 plus 1 divided by 2, 0 plus 1 divided by 2, it will never give us 0.5, it is equal to 0 because it is integer division. Therefore L is also here and R also fell over here, so L equal to R. Okay, this may be the position where the key may be found. If at all the key happens to be occupying the very first position, this particular iteration strikes that particular key and it will take it out. But here in this example, this is not equal to key. So therefore the algorithm will reduce R further. Okay, the earlier mid is 0, 0 minus 1 is minus 1. So R becomes minus 1 while L remains to be 0. Therefore L becomes greater than R, or R becomes lesser than L. This becomes a fictitious situation. So that is good enough for the algorithm to say that the key is not present. On the other hand, reversal will take place. If at all we want to search for a key which is maybe 89. So we will search for a key which is equal to 89. Let us see what happens. Okay, I think this should be clearly known before we write the algorithm. So key equal to now 89, which is not there. Okay, therefore once again in the first iteration, mid equal to 0 plus 6 divided by 2, that is 3. So mid is this. So here a of mid is not equal to key, therefore what happens? So the left extremity goes on reducing. So L no more remains to be 0. Okay, L will start from over here, it will become mid plus 1. Mid plus 1 means 4. But right extremity stands to be 6. Therefore before it goes for the second iteration, mid will be calculated, new mid will be calculated. It is 6 plus 4 divided by 2, 6 plus 4 divided by 2 equal to 5. So this is 3, 4, 5. So mid is over here. Again mid is not equal to, a of mid is not equal to key. Therefore once again the left extremity will be shifted to 5 plus 1, that is mid plus 1. It becomes 6, and R remains to be 6. And this may be, let us say if we were to search for 88, okay, L equal to R, okay, this case is also possible. That means the key may be resting in the right extremity, and in the other case, if at all 23 were to be the key, it will be resting in the left extremity. In that particular case, L will be equal to R. And if we calculate mid, once again mid will become equal to 6. Anyway, it's not equal to key. Okay, a of mid is not equal to key. Therefore what happens is L will be incremented by 1. So L will become mid plus 1, it is 6 plus 1, it becomes 7. So L will go over here, okay, the left extremity will go over here, and right extremity will be over here. So right extremity R equal to 6 and L equal to 7. This is again a fictitious situation. So the limitation for this binary search is it should be found anyway. If at all it is there, it should be found within the extremities, or within L or within R. Okay, anywhere within the array, or it could be present in the leftmost extremity also when L becomes equal to R, or it may be present in the right extremity also. In no case, if at all key is not present, L will become greater than R. Okay, R will take a negative value if at all the right extremity goes on reducing, and L will be more than R. L will become positive. It will be positively more than R if left extremity goes on incrementing. Okay, that is the thing, that is the understanding that you should have. So with this, okay, anyway if key is present, A of mid will be equal to key. So with this knowledge, we will go and discuss the algorithm. Okay, it is a recursive algorithm which is written over here. Okay, algorithm binary search. Okay, you need to name, you should not name it as 0 to R, because it will become very specific. Anyway, the first value, the first extremity and the last extremity. Okay, we should give a general name like this, because we don't know where exactly first will move and where exactly last will move. Okay, 0 will never remain to be 0, and the last element will never remain to be last element. Okay, the last position will never remain to be last position. Okay, last position will be usually decremented, and first position will be incremented if at all till the key is found. Okay, key is also to be supplied to this algorithm. It implements recursive binary search. Input an array first to last defined by its first and last indices, and returns the location where key is available, or -1 if key is not found. If first is greater than or equal to last, I should have written like this: greater than or equal to last, or greater than last, return -1. Yes, this is correct. It should be returning -1 if at all this condition comes true. Okay, this condition comes true. Yeah. Now else if this condition is not true, then mid equal to first plus last divided by 2 floor. Floor is taken with the guess that the array may be odd numbered array also. If key equal to array of mid, return mid. Okay, the position is definitely the middle position. Else if key is greater than array of mid, then return binary search. You call the binary search algorithm array mid plus 1. Okay, 2. Okay, the first left extremity will be shifted to mid plus 1, and the last will remain as it is and the key. Okay, else return binary search array first will be there as it is, and the last extremity will become mid -1 key. So this is the recursive call, and if we try to write the recursive relation for this, before a call is made, it makes one comparison. Therefore, number of comparisons in the worst case of the algorithm, okay, as a function of input size n equal to number of comparisons for only one portion of the array which has n by 2 as number of elements, plus one comparison before the recursive function is called. This is one comparison before a recursive. Every time this is the situation for the algorithm faces the same situation. Okay, every time the array sub-array, only one portion of the sub-array, only one portion of the sub-problem will remain with the size equal to n by 2 after one comparison. Okay, it could be any comparison, and number of comparisons, the base case for this could be, if number of elements are 1, there is no comparison at all. Okay, that is the middle element. So that is the element key that is being present, or it may be absent. Anyway, now we can apply Master's theorem. Here a equal to 1, there is only one sub problem that remains. B equal to 2, B will be equal to 2, and D equal to 0. D equal to 0, because we can assume this one to be the effect of n to the power of 0. Maybe n to the power of 0 equal to 1, then anyway D should be taken as 0. So this matches a Master's theorem. If you apply the Master's theorem, so this comes to a condition of, this matches the condition of a lesser than, a equal to b. Actually it falls under a equal to b to the power of d. A equal to b to the power of d. A is also equal to 1, b to the power of d. Therefore time complexity of binary search as a function of input size should belong to big theta of n to the power of d log n. N to the power of d is n to the power of 0, so it is 1, therefore log n would only remain. Therefore the complexity of binary search is log n. Okay, this is the thing that we need to realize. You can compare this comparison, this number of comparisons in case of binary search with respect to sequential search or linear search, where we proved that the complexity is n. Okay, that happened in brute force algorithm. The binary search, with due respect to the inventor, with the other names like half interval search and logarithmic search and binary chop algorithm, was invented by Donald Knuth in 1968 and given in Knuth's famous book titled The Art of Computer Programming. It is mentioned over there. Okay, we'll take another example, multiplication of large integers. Okay, anyway, the large integers, there may be situations, particularly in cryptology, wherein large integers are multiplied. Okay, manipulation of large integers are involved. Okay, and this large integers happen to be more than 100 decimal digits long. Since such integers are too long to fit in a single word of a modern computer, it becomes essential that we should find a different method, or we should be given a special treatment. This practical need supports investigations of algorithms for efficient manipulation of large integers. In this we will take this example and we will see how exactly this divide and conquer strategy would help us to find out to reduce number of multiplications. So we will take an example of 34 and 25, two digit numbers. Okay, if you multiply them, okay, it is 34 into 25. Okay, 5, see it is something like this, 4 multiplications has to happen. Okay, it is 2 into 4 and 2 into 3, 2 multiplications, 5 into 4 and 5 into 3. Okay, another 2 multiplications. Therefore, if the number of digits are n, it requires n to the power of n square multiplications. Okay, if number of digits are n, it should be n square multiplications. Anyway, we will understand the algorithm, application of the algorithm, divide and conquer algorithm, by this specific example. Then whatever that we discuss and whatever the formula that we derive, that recursive formula that we derive, or the efficiency case of this divide and conquer algorithm in terms for the application of multiplication of large integers, can be extendable even for any digited numbers. Okay, so for the sake of clarity and for the sake of ease, we have taken 2 digited numbers. Okay, 34 can be written something like this: 3 into 10 to the power of 1 plus 4 into 10 to the power of 0. There is no harm in writing this. 25 should be written as 2 into 10 to the power of 1 and 5 into 10 to the power of 0. When we multiply, instead of directly multiplying this, we will multiply this expanded version of 34 and 25. So 3 into 10 to the power of 1 plus 4 into 10 to the power of 0 into 2 into 10 to the power of 1 and 5 into 10 to the power of 0. Okay, 3 into 2 into 10 to the power of 1 into 10 to the power of 1. So it will become 10 to this 10 square. 10 square indexes are added. Okay, 3 into 5 and 4 into 2 into 10 to the power of 1. Okay, and 4 into 5 is 10 to the power of 0 into 10 to the power of 0. 4 into 5 into 10 to the power of 0. So 3 and 2, you can notice over here, 3 is the first digit of the first number and 2 is the first digit of the second number. And here 4 is the second digit of the first number and 5 is the second digit of the second number. and here 3 into 5, first digit of the first number, and the second digit of the second number, first digit of the second digit of the first number, and the first digit of the second number is coming over here. There is a pattern over here, but anyway it has not reduced the number of multiplications. The one multiplication, 1 2 3 4 multiplications are again there, and it will also give, this expanded version will also give the correct answer. Let us be assured about this. But anyway, incidentally or fortunately, the inventors have found, the inventor of this large multiplication of large numbers has found that the central term 3 into 5 and 4 into 2 can be expressed as something like this. So, okay, I repeat, the central term, that is 3 into 5 and 4 into 2, can be expressed something like this. That is the thing. Okay, yeah, we'll take this. So 3 into 5 plus 4 into 2 can be written as 3 plus 4 into 2 plus 5 minus 3 into 2 minus 4 into 5. So 3 into 2 is here. We have already found the answer, and 4 into 5 is here. We have already found the answer over here. So what remains to be found is only this much. Okay, there were 2 multiplications. Now it is reduced to only 1 multiplication. Only 1 multiplication in place of 2 multiplication and 1 addition. Okay, this expansion has found 1 multiplication and 1 addition. 1 addition remained, but there is an extra, okay, 2 additions, out of which 1 addition is already there. Okay, there is an increase in 1 addition and subtraction, 2 subtraction and 1 addition, apart from reduction of multiplication. Anyway, computers literally don't take in much of the time for addition and subtraction. They only take maximum time for multiplication and multiplication and division. Therefore, it is a saving. It's a saving in running time. So the number of multiplications for 2-digit numbers happens to be only 3 multiplications. Here 1, 2, and here 3. Okay, anyway, in order to formalize this particular example, or this large integer multiplication, we will take a notation. Let the first number be represented as a1 and a0. Here a1 is 3 and a0 is 4, and in case of b, it is b1 and b0. b1 is 2 and b0 is 5. Okay, if we say c equal to a into b, it would also mean c2 into 10 square, c2 into 10 square, where c2 is this one, and c1 into 10 to the power of 1, where c1 is this one, and c0 is this one. Okay, so we will explain these notations. C2 equal to the product of their first digits a1 and b1. Okay, like it happened, 3 into 2. And C2, C0 is the product of last digits a0 and b0, while C2 is the product, C1 is this, that is the product of sum of the first digit and second digit of the first number, and first digit and second digit of the second number. Okay, it is the product of sum of first digit and second digit of the first number and first digit and second digit of the second number minus C2 and C0. C2 and C0 have already been explained. Okay, right. Now C equal to a to the power of b. If same trick can be applied even to multiply 2 n-digited numbers also. Let a be n-digited number, b is also n-digited number. It could be written like this: c1 into 10 to the power of n by 2. Okay, a can be expanded as, okay, a into 10 to the power of n by 2. Okay, plus a0, b into 10 to the power of b1 into 10 to the power of n by 2 plus b0, a1 into 10 to the power of n by 2, because a can be written as a1, okay, consisting of n by 2 digits, and a0 consisting of remaining n by 2 digits, and b can be written as b1 and b0. b1 is the n by 2 digits, first n by 2 digits, and b0 is the last n by 2 digits. Anyway, a1 into b1 into 10 to the power of n, similar to this one. Okay, first half digits into 10 to the power of 2, because they are 2-digited numbers. therefore it came here as 10 to the power of 2, and here they are n-digited numbers, therefore it becomes A1 into B1, the first digits, first half of the digits, first whole of the digits of A1, the first whole of the digits of A1, B1 into 10 to the power of n, and A1 B0 plus A0 B1 into 10 to the power of n by 2, okay, simulating 10 to the power of 1 over there. For 2 digit numbers it is 10 to the power of 1 and it is 10 to the power of 2. For n digit numbers it should be 10 to the power of n and it should be 10 to the power of n by 2, and this is simply multiplied A0 into B0. Therefore C2 into 10, this can be generally expressed as C2 into 10 to the power of n plus C1 into 10 to the power of n by 2 plus C0, where C2 is A1 into B1 is the product of their first hollows consisting of 2 n by 2 numbers, and C0 is A0 into B0 is the product of their second hollows, that is consisting of n by 2 numbers for the half portion on the right side. Okay, C1 is this one, that is A1 plus A0 into B1 plus B0 minus C2 minus C2 plus C0. C2 plus C0 has been explained over here, and this is the reduction. Therefore it can be generalized now. Multiplication of two n-digit numbers requires 3 multiplications of 2 n by 2 digited numbers. 3 multiplications of 2 n by 2 digited numbers, because here A1 B1 is also n by 2 digited numbers, A0 B0 this is also n by 2 digited numbers, so it requires 1 2 and here 3. Okay, 1 2 and here 3. Okay, reduced version, right? So therefore we can develop a recursive relation something like this: m of n equal to 3 times m of n by 2. Okay, right? Okay, multiplication, number of multiplications involved for 2 n-digited numbers equal to 3 multiplications of 2 n by 2 digited numbers, and m of 1 equal to 1. Okay, if there are 1-digited numbers, number of multiplications equal to 1 only. Assume n equal to 2 to the power of k and do some kind of a back substitution that we remember. Okay, we can recall our memory. So m equal to 2 to the power of k, so 3 times m 2 to the power of k minus 1, because it is n by 2. Okay, 2 to the power of minus 1 will come up. Okay, k minus 1, so 3 into 3 into 2 to the power of k minus 2, so 3 square into 2 to the power of k minus 2, 3 cube into 2 to the power of k minus 3. So it goes on, okay, like this. But anyway, the pattern is found over here. Okay, in the second step it is 2 and it is 2. In the first step it is 1 and it is 1 over here. Therefore we can replace this pattern with I. Okay, this pattern with I. So 3 to the power of I into 2 to the power of k minus I. Okay. Okay. Then in order to make this to be 1, because the base case is 1. Okay, m of 1. Therefore in order to make it 1, we will substitute I equal to k. We'll substitute I equal to k. We'll substitute 8 equal to k. So I should be equal to k. If you substitute I equal to k, then what happens? 3 to the power of k and 2 to the power of k minus k. K minus k becomes 0. 2 to the power of 0 is 1. So 1 is 1. Therefore 3 to the power of k would remain. Okay. If n equal to 2 to the power of k, then k will be equal to log 2 log n to base 2. This is known to us log n to base 2. Okay, we'll substitute to the power over here. So 3 to the power of log n to base 2 can be definitely expressed as n to the power of log 3 to base 2. Okay, base exchange formula. Therefore it is approximately equal to n to the power of 1.585. 1.585. I think we cannot disregard telling that it is a small reduction, and we should note that this reduction happened. Okay, in case of pencil and paper algorithm, the number of multiplications involved for 2 n-digited numbers happen to be n to the power n square. It is n to the power of 1.585. There is a substantial reduction. Of course, we should keep it in mind that for moderately large integers, this algorithm will probably run longer than the classic one, because there is too much of calculations involved. Okay, and two inventors, Prasad and Bratley, have reported that This method will outperform the conventional methods when integers over 600 digits are considered. Okay, therefore this algorithm is proved to be very beneficial if the number of digits crosses 600. Okay, it brings in substantial reduction in the computer time or algorithm running time. Okay, therefore we have accepted, we have promised that a divide and conquer technique is applied, will be applied in multiplying the large integers. We did so because for n digited number is broken into two n by 2 digited numbers. Okay, there exactly happened the division. So we'll take another practical example. Okay, realistic example. So this is an example. We try to multiply 2101 into 1130. So here C2 is 21 into 11. Okay, multiplication of the first two integers. First, okay, this is the first part and this is the first part. This is the second part and the second part. First part into first part will also call for application of the algorithm, and second part into second part will also call the application of the algorithm. Therefore, in the first instance, C1 is 21 into 11. C0 is 1 into 30. Okay, 0 1 into 0 30. Okay, therefore C0, C1 and C2. Therefore C1 equal to 21 plus 0 1 into 11 into 30 minus C2 plus C0. Okay, C2 plus C0 is over here, and you can expand this, and this is to be multiplied again. Okay, this formula is to be applied again, 21 into 11 and 22 into 41 and 1 into 30. This should be applied. Formula is to be applied. For 21 into 11, we will apply the the divide and conquer strategy. Here C2 is first digit of this and second digit of first digit of this. So 2 into 1 will give us 2, and C0 is 1 into 1, that will be giving 1. Therefore C1 equal to, okay, the sum of the first digits of the first two digits of the first number and the second number and its multiple minus C1, C2, C1 and C0, C2 and C0. Okay, this is applied and we got 3 over here. And for 21 into 11, therefore we have 2 into 10 to the 10 square, 2 into 10 square plus 3 into 10 to the power of 1 plus 1, 231. It gives us 231. 21 into 11 by the application of the formula or by application of the method suggested will give us 231. Okay, for 1 into 30, this is 1 into 30, we'll apply the algorithm again. C2 is first digits, multiplication of first digits, 0 and 3, it will give us 0. C0 is 1 into 0, that will also give 0. Therefore C1 is 0 plus 1, 3 plus 0 minus 0 plus 0. It will give us 3. Therefore 1 into 30, 0 1 into 30 equal to 0 into 10 square, that is C1 into 10 square, C2 into 10 to the power of 1 plus C0 into 10 to the power of 0 or 10 to the power of 2, 10 to the power of 0 exactly. For 22 into 41, okay, we have 2 into 4 8, C0 is 2 into 1 2, and C1 is the formula that is suggested, it will give us 10. Okay, and if you apply this, if you expand this in the power of 10, okay, 22 into 41 will give us 8 into 10 square plus 10 into 10 to the power of 1 and plus 2. 2 into 1 is 2, 902. Hence 2101 into 1130 will give us 231 into 10 to the power of 4. 231 into 10 to the power of 4 because n by 2. This is n to the power of n. 231 n to the power of n, that is 21 into 11 is 231 into 10 to the power of n by n. Okay, this is n by 2 related expression, and this is into n to the power of 0, that is 130. So it will give us, upon simplification, it will give us, okay, this particular number. You can watch this carefully. Okay, go step by step, you will be able to multiply applying the formula. You have to try, okay, my esteemed listeners will definitely try this and you will find out the answer. How many approximate comparisons are needed to search a key in an array containing 100 elements by linear search and by binary search? Automatically it requires 100 comparisons in case of linear search because the complexity is n, and in case of binary search the complexity of log n, it may require just 6.6 comparisons because 2 to the power of 6.6 is 100 log n. Write a non-recursive binary search algorithm and analyze its complexity. You can do this. You can write this, so that is conventional program we have simply done in our junior semesters or in our lower semesters. Anyway, we have done this. Okay, this happens to be very primitive, and in this example written over here, we have tried for a recursive algorithm. Compute 2345 into 1234 by applying divide and conquer strategy. First break this and apply the formula, and you will get 23 into 12. Once again you have to apply the algorithm for multiplying 23 into 10, and 45 into 34 will also come. There also we need to apply the algorithm. Okay, with this I will complete. Okay, and this completes divide and conquer algorithm strategy and 4 examples that we presented, okay, for divide and conquer. So next I will return to this video tutorial with decrease and conquer strategy, the next strategy. Until then, bye.